I would like to introduce our next speaker and tutor, maybe. But this is Kareem. He is presenting the tutorial gNMIc, an intuitive gNMIc CLI and feature-rich telemetry collector. Kareem is a technology and architecture consulting engineer at Nokia and is coming to us today from Sunnyvale, California. Come on up, Kareem.
Thanks everyone for showing up after lunch on the last day. So today I'll be talking about gNMIc, which is a tool that started as a personal project or a pet project about three years ago. And after a few months, a lot of my colleagues that I shared it with convinced me to make it open and share it with the rest of the community. So with a quick show of hands, how many people heard about gNMI? Not gNMIc, gNMI, the protocol. How many people use gNMI today? Right. Okay. So for the next hour or so, I'll be trying to explain what gNMIc is and what it does, how it does it. I'll start with a quick refresher on gNMI, nothing too deep or too complicated, basically just getting the terminology right so you guys know what I'm trying to talk about. And then I'll have a couple of demos running gNMIc as a CLI and running gNMIc as a telemetry collector. All right. Okay. So it's no news to anyone. Everyone's network size is growing. And when your network grows, you quickly realize that you can't manage it the same way you did. So you don't manage 10 routers the same way you manage 100 routers. You don't configure them the same way. You don't monitor them the same way. So you realize that you need to change your tools or you need to change your methodologies. You also realize that you will get more data, and then you will also need more refined data. You will, instead of collecting your interface statistics every 5 minutes, 15 minutes, now you need to collect them every 10 seconds. Some people do even sub-second collection. So all that load is not that friendly on the router CPU. We better let the router do what it's supposed to do, routing, instead of pushing or returning statistics being pulled by SNMP, for example. So what gNMI does is reverting that logic. Instead of asking the router to return statistics, you let the router push the statistics to you. So it's a subscription-based model. You just send a subscribe request to the router and you declare or you tell what you're interested on and how you want to get it. Say you're interested in interface statistics and you want to get them every 10 seconds, or you want to get the interface status whenever it changes, not all the time. You don't want to know that the interface is still up every 10 seconds or every 1 minute. You want to get that notification when the interface status changes. Right? And when more use cases related to closed-loop automation that gets its data coming from streaming telemetry become more popular, you will need a more reliable way to deliver the statistics into your system so that it can properly act on it. So gNMI uses TCP or HTTP2 as a transport protocol, while SNMP, well, no, just does UDP. All right. gNMI relies on gRPC, HTTP2, and TCP for delivery or as transport. The service and the messages exchanged are defined in protobuf. Protobuf defines a couple of things: the services, so the RPCs that the client and the server will be exchanging. To be clear here, the server is the router, the client is whatever tool you're trying to use to talk gNMI to your router. gNMIc is one example of those clients. So gNMI, the service defines 4 different operations: capabilities, get, set, and subscribe. So capabilities let you know or discover the capabilities of your router, what version of gNMI does it run, what Yang models are supported there, and what kind of encoding it supports. Get does what it says. You get configuration or state from the router. Set, you change the configuration on the router, and subscribe lets you subscribe to notifications from the router, whether sampled subscriptions that you'll get every certain period, or on-change subscriptions. So gRPC is the client-server RPC framework that lets those operations flow between client and server. HTTP2 is used by gRPC to multiplex all those queries over the same TCP connection. So you can reuse the same TCP connection, the same gNMI client to send gets, sets, capabilities, and subscribe. You don't have to establish different connections to configure the router or subscribe to the telemetry notifications that you are interested on. It's a single TCP connection. Okay. And then this is kind of optional. It's not required by the gNMI spec, but in an ideal world, your configuration and state should be modeled, and the language of choice usually there is Yang, at least in the networking world. Okay. So again, gNMI relies on gRPC, and you will be able to do network management with gNMI, like getting configuration and changing configuration on the router. It's a use case that's often ignored in favor of streaming telemetry, but I wanted to put it out there just to say that there is more than streaming telemetry to gNMI. Right. So a few terms that I would like to, I guess, explain or agree on here. So a target is the device that runs the gNMI server. It's basically your gNMI server that the client will communicate with. The client is the system that uses gNMI to get data from the target, change data in the target, or subscribe to notifications from the target. The data schema is your Yang models, basically, and the data populating the schema. The configuration is what you're able to change in the router using gNMI. Telemetry is the notifications that you will get or that you will stream, or that the router or the target will stream back to you after you send a subscribe request. A path is a list of elements that define an object on your router, like interfaces, interface, Ethernet 1 is a path, or network instance management, admin state is a path, and that defines an object on your router that you will be able to query, change, or subscribe to changes on that object. Okay. So going back again to the gNMI service definition for RPCs, and capabilities, discovering the target capabilities, the gNMI version, the supported gNMI version, the Yang models supported by the router, and then the encodings that the router supports. Encoding here means what kind of format the values that will be sent back to you will be, how they will be formatted. Get lets you query configuration or state from the router. You'll be able to do a get state only, get config only, or get both. A set lets you modify configuration objects on the router. That's basically your your CLI equivalent. And subscribe lets you subscribe to notifications by defining a set of paths that you are interested on. Here I wanted to just note that the subscribe RPC is a bidirectional streaming RPC. That's what those two stream keywords mean. It means that the client can send as many subscribe requests as it wants to the server, and the server will send multiple subscribe responses. While capabilities get and set are called unary RPCs, where it's always one request to one response, and then the connection is closed, or at least the gNMI connection is closed. Okay, so what is gNMI-C to gNMI? So it's a client. C can stand for client, collector, or CLI. It's up to you. Pick the one you want. It's a command line interface first. It's also a streaming telemetry collector, and it also creates a Go API, so Go the language here. That's a wrapper around the Go library that's generated from the protocol buffer. It's just easier to use. I'll have a couple of slides towards the end showing how it can be used. And around 4 or 5 months ago, gNMI-C was donated by Nokia to Openconfig, so it kind of became the de facto client for gNMI. Okay, so starting with the CLI part of gNMI-C, there are, the commands that gNMI-C supports or that you'll be able to use are kind of split in two categories. You have the RPC commands. They map one-to-one to each one of the gNMI RPCs. So you get capabilities, get set, and subscribe commands with their own flags and their own features, in addition to some, what I would like to call utility commands that are supposed to make your life a little bit easier when you're dealing with a gNMI-enabled router. So prompt, as an example, there are more than these three. But prompt, for example, just starts a prompt for you and helps you with auto-completion when you're using the CLI. If you start prompt with a Yang model of your router, it will even auto-complete the XPath for you, so you don't really have to guess, or at least it will try to help you. Generate has a few sub-commands under it, but the main idea there is to feed in the Yang model of your favorite router to gNMIC, and it will generate all the possible XPaths that you can get from the Yang model. It will also generate configuration payloads with defaults. It will generate them in either JSON or YAML, and you'll be able to go and edit them and push them towards your router. Diff is literally a diff, so you define a reference router and one or more other routers that you want to compare to that reference router. So that's, and it will tell you exactly what changed or what is different in the other routers compared to your reference router. It's very handy if you're trying to configure stuff like routing policies or ACLs, and you want them to be the same on all your routers. Okay. So gNMIC, you're able to configure gNMIC in different ways. The obvious or first one that people get to is using CLI flags. So there are two types of flags. There are global flags and local flags. The global flags apply to all the commands, and they usually relate to how you're connecting to the router. Nothing specific to the RPC you're trying to run or the command you're trying to run. So global flags are like username and password, your TLS certificates, the timeout for the connection you want to establish to the router. The local flags are specific to the command, like the path you want to get from the router or the type of the subscription you're trying to establish. So here's an example of a command. So this command will connect to router 10.0.0.1 with username and password admin. It will not attempt to verify the certificates shared by the router, and it will try to get the path or ask the router to return whatever interface management 0 has under it. You can do exactly the same thing with environment variables. You either export them beforehand or you source them from a file. You run the same command. Here I only put the global flags as environment variables, but you can do the same with local flags as well. And you can mix and match. You can do some flags, some environment variables. And the last way is configuration file. That makes it repeatable. You'll be able to share it with your colleagues, customers, and so on. So the global flags are on the main level of your YAML file, and then for each subcommand, you'll be able to do get path and specify the path there. You run the gNMIC command with the flag config. You pass in the file, you run your command, and it will do exactly the same thing. You can also define the file in JSON format or HCL, but YAML tends to be the more human-readable one, at least for me. You can, again, mix and match CLI flags, environment variables, and file configurations. The CLI flags will take precedence over the environment variables. The environment variables will take precedence over the config file. So you can reuse that config file and override values that are there using the CLI, the flag, or the environment variables. Okay. So there is more to the configuration file if you're running gNMIC as a telemetry collector. So you'll be able to define your targets, so your routers, under a map in your YAML file. You define the subscriptions, the outputs, where do you want to write the results or the notifications that you received from your router. You'll be able to define processors to do basic data manipulation if you want to convert a counter that you're receiving as a string from the router to an actual integer that you will want to write to a database. You can do that there. And you can also cluster multiple instances of gNMIC together where you will be able to share the load between them and they will auto-discover each other and orchestrate which instance subscribes to which router. All right. So, like I said, the CLI flags take precedence over the file. So if you have a target defined or multiple target defined in your file, but you want to run a quick test on one of the routers, if you use the flag address or -a, the shorthand, you will be able to run whatever command only on that target, even if the file contains multiple targets. So that's how the address flag overrides the target map in the YAML file. Or you just run subscribe, and it will subscribe to all the targets defined in the file. Okay, so it's a different font. Okay, so going into capabilities request, or we'll go through the commands and RPCs one by one. So again, with the global flags, you define how you want to connect to the router, the address, username, password, whether you want to define TLS certificates there or not, or just establish an insecure connection, which you shouldn't do in production. But for a lab, it doesn't really matter. Capabilities command, and you will get a response that looks roughly like this. So again, the gNMI version, the list of supported Yang models with their revisions, and the list of encodings that the router supports. For a get command, it looks the same. The CLI tries to follow the protocol buffer definition. So if you go and dive into the gNMI proto file and look at how a GET request looks like, you will be able to map each field in that GET request to a CLI flag in your command line. So the prefix is flag prefix. Path is a repeated field here, so you can specify multiple paths. You'll be able to specify multiple path CLI flags. Same with data type, and same with encoding. So it's fairly easy to guess what kind of flags are there if you look at the message structure. So running a get command, you will get a notification response in a get response message that has the path and the value that you asked for in your command. Here, you can also change the format of the response, or how the response is printed out in the terminal or in the file, if you want so. So here you see a prototext format. It's a little bit too verbose. It's not the default format, but it tells you, it would show you exactly what the router sent back. Okay. Set command lets you run a set RPC against your router. So again, going to the set request proto message, you can map each one of the fields there to a CLI flag. So in a set request, you send a prefix, a path prefix that will apply to all the other paths. You can delete values or objects in your router. You can replace them, or you can update them. The delete, replace, and update will apply in that order. So delete, replace, then update. And if one of them fails, the whole thing fails, meaning that a single set request is treated as a single transaction by the router. So there is no concept of candidate data store. There is no concept of merging your candidate into your running config, kind of like in netconf. And an update message, so whether replace or update, is made of a path and a typed value. So the path points to the value you want to change, and the typed value will be the value that you want to update there. And typed value means here that you can have multiple types. So it can be a string, an integer. It can be even so it can be a JSON blob as well. So here's an example of a set request. You can send so you can use update path and update value to create the update object or message that we saw in the previous slide. And here you have to specify the encoding that tells how that value needs to be encoded, or what type of value, or what kind of typed value needs to be used when sending the update value enable to the router. The response looks like a list of results, so which operation type, update, delete, or replace, and then which path was changed. So this is doing set requests inline, meaning that all the paths and value for update, replace, or delete are set using a flag. You can also use a file if you want to update multiple values at the same time. So, or update a more complicated payload that you want to, configuration payload that you want to send to the router. So it's easier to use an update file or a replace file here. So in JSON or in YAML again, if you're dealing with multiple nested objects or leaf lists, rather than setting them on the CLI. Right. With the set command again, so we're still there, you can also define a single file, again in YAML or JSON, both work, where you define all your replaces or your deletes and all your updates in one go. The file is also can be templated. gNMIc will render it per target, so you can define variables specific to different targets, and gNMIc will render the template and send different requests to each one of the targets. So you can do kind of like Ansible style configuration with gNMIc set. Now the subscribe command. So like I said at the beginning, so it's subscribing to the routers on object that you're interested on, either periodically or on change. gNMIc will get all those notifications, process them if there are processors defined, and it can write them to multiple outputs. So outputs are, say, generally or fall generally in 3 different categories. So either a database, FluxDB, or Prometheus are the most popular TSDBs that are used with streaming telemetry. You can write it to a message queue. gNMIc supports Kafka, NATs, all flavors of NATs, so Jetstream, Stan, that's deprecated, and pure NATs. Or you can write it to a file or just dump the results to a terminal for you to read. There are a few other outputs that are supported that don't really fall into any category. The most notable one, I guess, is the SNMP output. So gNMIc can subscribe to gNMI updates or notifications from the router and build SNMP traps out of that, or mapping gNMI to SNMP traps. Okay. So the subscribe command is a little bit more involved, since you have more stuff to define. So the same global flags, subscribe command, which path you're interested on, and how you want to get it. So there are 3 types of subscriptions, or 3 main types of subscription. You can do a once subscription, meaning subscribe, return all the data, then just close the connection. A poll subscription, where you set what you're interested on, but you will only get a response when you send another poll message. So you can poll whenever you want from the router. Or a stream subscription, which has 3 subscription types. So a stream subscription can be sampled. So using a sample interval, you can define how often you want to get updates from the router or notifications from the router. A stream subscription can also be of type onChange. So whenever the value changes, send me that update. Otherwise, no need. And there is a target-defined, or what's called a target-defined stream subscription, where you basically let the router decide if it wants to send you that value on change or in a sampled way. So in this example, you will receive the interface counters every 10 seconds. Or you can subscribe to the interface operational status whenever it changes. You don't need to know that the interface is still up. You only want to know if it goes down or goes up if it's not supposed to be. Okay. So going to the generate command. So generate, again, allows you to generate configuration payloads out of the Yang model of the router, or generate XPaths that you will be able to plug in into get, set, or subscribe command. So this shows how to pull the Openconfig Yang models and run the generate command. This will generate the YAML payload that you'll be able to use as a configuration and send it to your router. So it will generate something like this. You can go and edit it manually if you need. You can also select a path and it will only generate whatever is under that path, not the whole configuration defined in gNMIc. So generate has a subcommand called generate path, takes exactly the same flags, and it generates a list of all the possible X paths that the router supports. You can filter them by config only paths, state only paths, if you're interested in that. Okay, so I'll start with the first demo. The goal here is to run the few basic CLI commands, see how to run a capabilities command, a get, a set, or a subscribe command from your terminal. I'll deploy a simple topology here, so 2 leaves and 1 spine, and show how to run those basic commands and modify some configuration on the router. Okay, so all the commands and the files that I will be using here will be in a GitHub repo. The link is in the presentation in one of the slides somewhere. Okay, so I'll start by deploying the topology. So again, 2 leaves and 1 spine. I'm using Container Lab. I don't know if you've used it before, but did a presentation of Container Lab, I think 2 or 3 nanos ago. Go check it if you're interested. All right, so what we got there is, so 3 nodes, again, 2 leaves and spine, their IP addresses, and they're up and running. Okay, so I'll export the router password as an environment variable. You don't necessarily want to have it in your history. So this first command is a get command, connects to leaf1 and gets the host name. As simple as that. If I run it, you get there your response, and it says basically that the host name is leaf1. You can do the same with a different path. So if I'm interested in looking at Ethernet 1 or Ethernet 1/1 interface, I get a bunch of information there. I get both config and state from that router. If I want to filter out only config, all I have to do is type config or -t config, and I'll get just the configuration that's set under that interface. So all these commands you can also run to all or towards all the routers at the same time. So if you look at, or if you can see the address flag over there, I have a comma-separated list of routers. So gNMIc will go and run 3 get commands, 1 to each of the routers, and you'll get the interface config or the interface admin state of Ethernet 1/1 on the 3 routers. So going into set command. Okay. So this command will enable or make sure the admin state of Ethernet 1.1 is set to enable, and that a subinterface of index 0 or with index 0 admin state is also enabled under Ethernet 1/1. And it will do that in both leaf1 and leaf2. Note that subinterface index 0 doesn't exist yet. What the router will do, or what the gNMI server will do or should do, if it's properly implemented, you should go and create that subinterface if it doesn't already exist. Okay, so that I guess worked. And if I run a get command there, so I'm running that on leaf2, and I can see that the subinterface index 0 was created. If you remember the topology, spine 1 had 2 interfaces, so Ethernet 1/1 and Ethernet 1/2. I can configure both with a single command and create subinterfaces under those 2 interfaces with a single gNMI set request. Running a get, I can see that both interfaces have that subinterface created or set. So like I said in the slides, you can also configure or send configuration payloads to the router using a file, a JSON or YAML file. So if I want to create the same or create the same config. So enabling an interface and creating a sub-interface under it, I can do it with a file that looks like this. All I have to do is just, instead of using update value, I just use update file. It's like this. And since the config will look the same under both interfaces, I can reuse the same file as a value to enable the interfaces there. Going to subscribe. So I'll be using the same topology. So since I configured my interfaces, now I should start monitoring those interfaces. So I want to get the statistics of Ethernet 1/1 from leaf 1 every 10 seconds. So if I run that, I'll get the first payload, which has just the list of all the counters that that interface supports. And then within 10 seconds, I'll get it again. So every 10 seconds, you will get the same counters. I can do stop it. I can do it a once subscription. So I'll get the response once, and it just stops. So one interesting thing to note here is this is essentially the same thing as a gNMI get, right? There are a couple of differences. So with gNMI get, you can filter out config or state or both. With subscribe, you cannot do that. And with a subscription, so if you remember, subscribe is a bidirectional streaming RPC, which means that both the client and the server can send multiple messages within the same stream. So a subscribe once is actually a better get than get if you're pulling a lot of data, because the router will be able to split it into multiple responses, not sending you the whole config in a single response. And subscribing with a config file. So if I look at this example configuration, so I have 3 global flags: admin, the password, and skip verify. And I set 2 subscriptions, getting statistics from both interfaces every 10 seconds. So the way I would use this is, so specifying the targets, so the 3 nodes, the config file or the path to the config file, and the subscribe command. If I run this, I'll get both subscription data every 10 seconds. Note that leaf 1 and leaf 2 don't have an Ethernet 1/2, but the subscriptions still don't fail. You just will not get any data from them. Okay, so I think that's it for the first demo. Whatever I did here is also available on the slides. I should have started with this. This is how you install gNMIc. Should have clicked one more time. So there's a script that you can get from that URL, and that allows you, or that will install gNMIc in your system. If you don't trust that script, you can go to the GitHub repo, download the binary manually, and place it wherever you want. Or you can pull the Docker image, use it as a CLI or a collector. Okay. So I'll skip all these. That's the URL to the GitHub repo. Going into the telemetry collector part, so gNMIc is not just a CLI again, it's also a telemetry collector that's also highly, or can be made highly available via clustering and load balancing. So it will grab the subscription data you tell it to do from the route, or to get from the routers, write it to a TSDB, and then you'll be able to plug in Grafana or Kibana or any visualization dashboarding tool that you like. Pull that from your TSDB. Prometheus or Influx are usually or InfluxDB are usually the obvious choices. So the way you would do that in the configuration is you have to define your targets. You have to define your subscriptions, bind them to the targets. You have to define your outputs and bind them to the targets. So the way you define targets is by like what you see here on the left side of the slide. So under targets, give them a name, address, username, password, how to connect to the router. Basically, there is more than this. You can set the TLS version. You can set the preferred TLS version. You can enable gzip if you're expecting to receive a lot of data. And then under the targets, you can also bind subscriptions and outputs by name. We'll see that in the next few slides. If your targets change frequently, gNMIc can also go and discover them dynamically. So you don't have to rewrite or update this file whenever something changes. You can get gNMIc to discover your target. So there are a few ways to do that, either from another file. So whenever that file changes, gNMIc will reload the list of targets, remove the ones that are gone, and add the new ones. It will not detect changes in configuration. So the way to update a target is to delete it and then add it back. You will be reestablishing the connection anyways. So you can discover it via an HTTP address, so an arbitrary API. So you can define the URL, the payload. You can define a template that will be used to transform the data you receive back from whatever system you're getting the list of targets from, so that gNMIc can understand them or load them. And you can also discover routers or targets from console. So you just tell it which services to watch. It will get the instances of that service and try to subscribe to them as gNMI targets. The fourth way of discovering targets is based on Docker. So this is usually not useful in production, but it's useful when you're doing labs. Your routers are either running as Docker containers or as VMs. You'll be able to discover them this way, and you can filter them with whatever labels were placed on that container when it was created. So the filters there are basically just like running docker ps-f and then filtering with whatever labels are there. Okay. So the way to define subscriptions, I think we've seen this in the previous demo. So under subscription, you give the subscription a name, the list of paths that you need to subscribe to, and the type of that subscription, whether it's a stream, one subscription, whether it's sampled, on change, or target defined, the encoding of the values that you want to get back from the router. There are a few other options there. So for a sample subscription, heartbeat interval says that on top of sending the values every sample interval, so 10 seconds in this in subscription one, also send it every 60 seconds. And suppress redundant means that don't send the value if it didn't change. So that suppress redundant only applies to the sample interval. It doesn't apply to heartbeat interval. So if you want a sampled subscription, but you still want to, I guess, save data, you can tell the router to not send data if it didn't change, but still send it every heartbeat interval, regardless whether it changed or not. The second subscription is a stream on change subscription. So you will get the interface operational status whenever it changes. But if I don't get any notification from the router, does it mean that the interface state didn't change or that my router is down? So you can set the heartbeat interval there, and you will still be able to get, or you'll still get the operational status of that interface every 60 seconds, whether it changed or not. So you get kind of a combination of both an on change and a sampled subscription in one. Okay. Slides are a little bit messed up. So the way to bind subscriptions to targets, so subscriptions are named. They have a name, sub1 and sub2 in this example. You can go under the target definition, subscriptions, and you list the subscriptions that you want that target, or that you want gNMIc to subscribe towards that target. So sometimes you have routers from different vendors, the models are different, the paths are different, behavior can be different. They support different sampling intervals, for example, so you want to map different subscriptions to different targets. If you don't put any subscription under the target, gNMIc will go and subscribe to every subscription defined in the file for that target. So if you have a simple use case, so routers from the same from the same vendor, same version, same Yang model. You don't have to define that. You just make that implicit. Okay. So outputs. Again, gNMIc can write to multiple different types of outputs. So InfluxDB and Prometheus, the TSDBs are usually what you see used. But then with like closed loop automation use cases, it makes more sense to write that data into a message bus. That's our Kafka, is what's supported by gNMIc, and you have a subscriber or a subscriber to that message queue on the other side, ingesting that data and acting on it. You can write to different outputs at the same time. You can set different subscription to be written to different outputs. So you don't have to write everything everywhere. So you can collect once and reuse multiple times. So you can have the same subscription used for monitoring, for dashboarding, but still that data is sent into a message queue and another system picks it up from the other side and acts on it. Okay. So the way to define output is very similar to subscription. So under outputs, you give it a name, a type, and then you bind it to the target if you want the subscriptions of that target to go to that specific output. So what gNMIc will do is get that gNMI notification, store them, and make them available to the output. If the output is pool-based, like Prometheus, Prometheus will send a scrape request every 10 seconds by default. gNMIc will have those notifications ready to send back to Prometheus. With other outputs like InfluxDB, where you have to push the data or write the data into the database, you can set a write interval every 10 seconds, every 30 seconds. All those messages will be buffered until the timer is reached, and then everything is dumped into the database periodically. It also supports Prometheus push mode, so you can do both. So processors, you can do basic data manipulation with gNMIc. You can change the type of the values you receive. Like a very common use case is changing strings to integers. If you're dealing with counters, some databases will not take it or will not figure that out. You can group messages together to, I guess, add labels to your interfaces or add more context to the statistics you're trying to collect, like adding the description of the interface to the statistics. You can enrich the message from whatever else you want. You can add arbitrary values there. You can add arbitrary labels. You can filter. So if for some reason you're subscribed to a path and you're getting too much information, you can just delete some of the counters you don't really need. You can only allow specific ones. And the third type of processor is called a trigger processor, where you can trigger an action whenever you receive a certain message. So this helps you with very basic closed-loop automation use cases. So whenever you receive a notification that says interface is down, you can trigger a gNMI get, a gNMI set, or another gNMI subscribe. You can trigger an HTTP request towards, I don't know, an alerting system saying that that interface is down. You can run a script locally, or you can take all that data, render a template against that input, and that, I guess, gives you another file that you can act on. Like one of the examples in the documentation website is subscribing to LLDP notifications from your routers, building kind of a topology out of that, and using a template, generate a container lab topology file that you go and run, and you basically just cloned your network into your server as containers. So just go check it and give it a go. And so processors are added under outputs, so you can have, so the processor will be specific to your output. So you can have a subscription that you want to write to two different outputs, but then you process those messages in a different way, whether you're writing them to output 1 or to output 2. So again, in the same idea as collect once, use multiple times. So you can filter certain values to go into the TSDB, but everything else goes into the message queue. So the next demo is showing how gNMIc works as a telemetry collector. So what I will be deploying is the same topology, a gNMIC instance, Prometheus, and console. Console is not necessary here. I just use it for Prometheus to automatically discover gNMIC, so I don't have to put the static IPs or host names of the gNMIC endpoint into Prometheus. Prometheus has that really nice feature where it can discover anything from anywhere, basically. Console is just easier to use for me, and gNMIC can register its Prometheus output into console, so you can just tie the stack altogether easily there. Okay. Yeah, maybe I go through the slides first. So the config file I'll be using looks like this. So 3 targets, leaf1, leaf2, and spine1, a single subscription, so all interfaces statistics every 10 seconds, and sorry, a single Prometheus output that will register itself into a console server that's also deployed together with a topology. So target definition, subscription definition, and output definition. Okay, so I'll deploy the topology again. And now it will come with 3 more containers. So the gNMIC container, the console container, and the Prometheus one. Okay, deployment is done. If I query or scrape the gNMIC Prometheus endpoint there, so /metrics, to get all the metrics that Prometheus would be getting as well, I can see that there are a few metrics in there. So it's each interface in octets and out octets for each one of the targets, so leaf1, leaf2, and spine, and the subscription name is added as a label there as well. Now, if I query Prometheus, just to make sure that the metrics get there as well, so there's prompt tool, I query, so I pointed to the Prometheus server, and I query interface statistics in octets. From leaf1, I should be able to get a couple of interfaces, so Ethernet 1/1 and the management interface. If I do the same query towards spine1, I get 3 metrics, Ethernet 1/1, 1/2, so the 2 connections to the 2 leaves, and the management interface. Okay. So from here, you can deploy a Grafana server, hook it into Prometheus, and start building dashboards. What I didn't show, or what I actually did without showing it, is that there is a filter applied to that subscription. If you look at the subscription path, so it's interface statistic, meaning give me all the counters, all the interfaces. But in the CLI, in the curl request or the prompt tool command, we saw only in and out octets. So those were filtered out by the processor. So any value with a name that matches any of those regular expressions there will be deleted or filtered out. So clustering, I'll try to explain how kind of works. So gNMIC is highly available, or can be made highly available, a highly available collector. You'll be able to scale it out. So there's literally no limit on the number of instances that you can run. The instances will discover each other, and a leader will be elected, and that leader will be responsible for assigning the targets to the different instances that it discovered. So gNMIC relies on a service registry to build the cluster. So each gNMIC instance, if it sees that there is clustering configuration in its configuration file, it will register its REST API as a service in the service registry, which can be either console or Kubernetes. Kubernetes is only supported when gNMIC is running inside the cluster, so it can't use a remote cluster to do clustering, so you have to be running within Kubernetes already. So each gNMIC instance registers itself in there, and the other instances can query and discover basically each other. So the way you configure it is enable the API server, so that's an API HTTP server. The clustering says what type of locker or what type of key value store you want to use to build the cluster. So in this example, it's console, the address of the console server. Kubernetes, it would just say Kubernetes. You already know you're running within the cluster. So the first step is the leader election. So all the gNMI-C instances will attempt to lock a specific value. So /gNMI-C, the cluster name, and then leader. So all of them will try to do it at boot time. The first one that manages to lock that value becomes the leader. So gNMI-C3 or instance 3 here is now the leader. The other instances will continue to try to acquire that key in case gNMI-C3 or the third instance either dies, restarts, or is taken out of the cluster. One of the other instances will take over as a leader. If you're using Kubernetes as a locker, the lease resource is used as a key lock. So instead of locking a value in a key value store here, like in console, you will create, or gNMI-C will create a lease resource in Kubernetes that defines how long that lease is valid for. Other instances will be able to query it and see if that instance is still alive or not. Okay. So once the leader is elected, it will read its configuration to find the targets or discover them, with whichever way is configured there. So Docker, HTTP, file, or console again. It will go through the list of targets one by one and assign them to the other gNMI-C instances running within the same cluster. The way it assigns them is by looking at how many routers are already handled by that instance and just take the least loaded instance and assign the target. It will not consider the number of paths within a subscription. It will not consider the number of subscriptions towards that target. So it's just the number of routers that the gNMI-C instance is handling. When gNMI-C receives a request or gets assigned a target, it will first go and lock a value in whatever locker is configured there. So again, console or Kubernetes, it will try to lock /gNMI-C cluster name /targets, the name of the router or the name of the target, and puts its host name or instance name in there saying, I claim ownership over this router. I will attempt to subscribe to it. It will keep that lock alive. It will not let it expire. If it disconnects from there, it will just let that lock expire, and then the leader will detect that and assign that router to a different instance. Okay. Moving on to different topics. So dial out telemetry. So there are two ways of dialing in your initial connection to do a gNMI subscription or a gNMI get or set. There's the dial in, setting up the gRPC connection from the client towards the server. And then once that's set up, you start sending your gNMI requests. Dial out works the opposite way. So the connection is established from the router. So basically the router dials out to your client, which is now a server. Then once that's established, the client will start, or the gNMI client will start sending gNMI requests over that established gRPC session. All right. So this is done using another project called gRPC Tunnel. So what it allows operators to do is, instead of allowing clients or systems to connect to their routers, like going into the network and having to open firewall ports there, or potentially creating security issues, it lets the router dial out back to the collector saying, I am here, I am so-and-so, and I have these capabilities. The collector from the other side or the gNMI client on the other side will use that established gRPC tunnel, RPC, to send the gNMI requests within it. So it's basically tunneling gNMI within a gRPC tunnel RPC. So the way you do this is by defining a tunnel server in the gNMI-C config file. It's as simple as setting which server address it needs to listen to. And then if you want to use it, gNMI-C, you just add the flag use tunnel server. gNMI-C will first wait for routers to dial out to it and then send the subscribe request over that tunnel. You can combine both a tunnel server and a gNMI server. So gNMI-C can also act as a gNMI server to which you can send gNMI requests, and it will kind of proxy them towards multiple targets. So you can send a gNMI RPC there, and it will tunnel it over the gRPC establish gRPC tunnel and send it to the correct gNMI server. So you enable both tunnel server, gNMI server, and then you specify the router you want to reach using the target flag. Okay, so there are a few deployment examples in the documentation. You can go check them out. They all come with a lab and configurations. So you can write to Influx, to Nats, to Prometheus, or to write everything everywhere all at once if you want to. Not saying this is an actual use case, but you can do that. There are also examples with clustered instances. So you can run multiple gNMIC instances, getting Prometheus to scrape from there. You can run kind of a tree of gNMIC instances or servers. So you have one instance that subscribe to the other instances, and you get all your data in one point, if that makes sense to you. I'll sadly skip this. Talk to me about it if you're interested. I'll get to the last slide. So if that sounds interesting, check the documentation portal, check the deployment examples. If you see something missing, you see a bug, you have an idea, there are issues and discussion on GitHub, go there, ping me or tag me, and give the repo star and grab a gNMIC sticker from there if you'd like to. Great, thank you.
We do have some time for some questions if people want to ask Kareem any questions. We have one. Can we turn up the mic?
Hi, I'm Tyler Bigler from the Home Depot. Can you talk at all about how the scaling works, like number of messages or devices per instance, so that you could sort of plan your scaling story for this?
It's a hard question.
Yeah.
Because there are so many things to consider. Not every router is the same. Not every subscription is the same. And if you play around with different encodings, you might get a different number of messages for the same data that the router is streaming back to you. So there is really no numbers, because
Slowly and carefully.
yeah, that's how I would do it. I would run as many instances as I can, just to minimize the impact if something goes wrong. Right?
Sure.
So you don't have to send all your telemetry to one single container or binary running in one single server somewhere in your network. Like, there's no reason to combine everything or do everything everywhere all at once, like I showed.
Yeah.
But in a lab, why not?
Thank you.
No other questions? If we can get another round of applause to Kareem here
Thank you.
for this wonderful tutorial.